purpose of this video is to introduce software JECP/HOLZ, a computer program for simulation of high-order Laue zone pattern, or briefly, HOLZ pattern. This is one of components in the Landyne suite for electron diffraction simulation and crystallography analysis. You may download the software suite on Landyne website. Paper about the previous version of the software was published in Journal of Applied Crystallography in 2005. The theories and formulas was presented in Journal of Materials Education in 2007. Here is the Landyne launcher icon. Double-click the icon to activate the launcher. If you have a license file, please copy the license key to C/Landyne3/programs/. This is HOLZ 2T and the license key. Click this button in the launcher to start HOLZ 2. A license dialog will pop out. In case you don't have the license file, then you may select the demo mode to continue. Let's start with the functions on the menu bar first and then go to details with examples later. In the drop-down menu, File, you may prepare a new structure data, or load a structure data for simulation, or save the simulated HOLZ data. The last choice, exit of the software. In the drop-down menu, Fine-tune, you may define a constraint of lattice parameters. In order to make a slight adjustment for simulation, you may select an advanced formula in simulation to take in an account of dynamical diffraction effects. In the drop-down menu, Display, you may display a HOLZ pattern in two approximation methods, either consisting of arcs or straight lines. You may display a whole pattern including both zero-order Laue zone and first-order Laue zone. You may define the parameters for output, such as region of interest and pixel per inch. The display can be saved in TIFF image and JPEG image. In the drop-down menu, Index, you may adjust both the index locations for the HOLZ pattern and the converged beam diffraction pattern. You may convert between Miller and Miller-Brevet indices for a hexagonal system. In the drop-down menu, Table, two tables can be selected, the periodic table of the elements and a table of space group symbols and numbers. The resources to help you to prepare a new input data of a crystal structure. In the drop-down menu, Option, you may hide or reselect the graphical menu bar. You may select one of the three look and feel options. In the drop-down menu, Help, you may get the serial number of the current drive. Send us the snapshot of the current drive dialog. We will use the serial number to prepare the license keys for you. In order to use the most recent version of the software, please visit Landyne's website regularly. Check and update to the current version. A list of crystal structure data is packed with Landyne software suite. You may use the data immediate for testing run of the Landyne suite. You may prepare a new structure data with an assistance tool. Simply fill the required data in a template and save the structure data. You may also edit in previous data in any text editor. The structure file is not complex. However, the format must be the identical when you edit a data using a text editor. In order to avoid any mistakes, we suggest you to use the template to create a new structure file. SVAT2 can be used to display the structure data, to check if the structure is correct. In addition, you may convert structure data directly in CIF format in SAVT2. It will save your time in preparation of a new structure data. Let's use the default structure, aluminum, to make a demo of the HOLZ2. Get a HOLZ pattern. All you need to do is to simply click Calculate button. The simulation is done under the conditions of default parameters. Let's change the parameters and do it again. Change the high tension from 200 kV to 100 kV. The HOLZ pattern changes. Change back to 200 kV. And change the zone axis from 100 to 110. Change the zone axis to 111. Change the beam angle alpha. The radius of HOLZ pattern changes. Change the beam tilt angles, X and Y. The position of the pattern shifts. Change zoom. Rotate. Intensity threshold. It may be helpful in matching to an experimental HOLZ pattern. Change lattice constraint. And lattice parameters. It allows to check the HOLZ patterns after small amount changes in lattice parameters. Change the appearance in arc. And straight line. It is the results of the approximation in two different models. Fine-tune of the calculation including dynamic effects. Now let's view the convergent beam electron diffraction hole pattern. Next, let's label the indices of the HOLZ pattern and convergent beam diffraction hole patterns. The default display mode is the HOLZ pattern with straight lines. The index scheme only works for straight line mode, not on the arc mode. Select the index scheme of HOLZ pattern in the graphic menu bar. Check Index on to show the indices. You may have tilted indices on left, right sides or up and down sides. You may adjust the positions of the indices. Change display mode to the convergent beam electron diffraction hole pattern. Select the index schemes of the hole pattern in the graphic menu bar. The other choices are intensities, basic vectors, Laue center. You may adjust the positions of the indices. For hexagonal system, both Miller or Miller-Brevet indices can be used. Click the hexagonal system in drop-down menu, Index, to activate the dialog. Select either reflection index or zone axis label, then click left or right arrowhead to make a conversion. Let's use the demo data. Clear the Miller-Bravais reflection indices field. Click the right arrowhead. Clear the Miller reflection indices field. Click the left arrowhead. Clear the Miller-Bravais zone axis labile field. Click the right arrowhead. Clear the Miller zone axis labile field. Click the left arrowhead. The simulated patterns can be saved to files in TIFF and JPEG formats. A region of interest should set up first. In drop-down menu, Display, click on ROI and TIFF. Check on ROI. A blue square will show up. Only display inside the square will be saved to a file. The size of ROI can be adjusted. For TIFF image, pixel per inch is needed to be set up. The default value is 300. Thank you for watching. Please check other videos on the Landyne software suite for electron diffraction simulation and crystallographic analysis.